So good evening guys. So in this video I'm going to be discussing the problem paint the tree that appeared in the Codeforces around 947 diff 1 plus diff 2. So in this problem they have given us a tree. Initially all the nodes in this tree are colored white and they have given us two chess pieces. Initially the chess piece PA is located at the node A and the chess piece PB is located at the node B, and they have given us a step. In each step we can do the following operation. In each step we have to move PA to a neighboring node and PB to a neighboring node. We can move PA to any of the neighboring nodes of PA, and we can move PB to any of the neighboring nodes of PB. And initially all the nodes are colored white, and when we move PA to a node that is white, PA will turn that particular node to red, and when we move the chess piece PB to a node that is already red, it will turn the color of that node to blue. But if we move PB to a node that is white, it won't affect the color, and if we move PA to a node that is blue, it won't affect the color. Only if we move PA to a node that is white, it will change the color to red, and only if we move PB to a node that is only if we move PA to a node that is white, it will change the color, and only if we move PB to a node that is already red, it will change the color to blue. So, and in the question they have asked us to find the minimum number of steps required to paint all the vertices blue. So there are actually two observations that we have to make in this problem. The first observation is that we will be using only PB can color the nodes as blue, right? So we will be mainly working with PB. We will also work with PA. So we have to minimize the number of steps that PB takes to reach all the nodes. Since PB is the one that is coloring the nodes as blue, the observation is that we will have to anyways minimize the number of we have to make PB go to every node, right? Since PB is the only one capable of coloring all the nodes as blue, we have to make PB go to every nodes. So that's one observation. PB has to visit every node, since PB is the only one capable of coloring the nodes as blue. But to make for PB to make it blue, it should already be red. That and making it red is possessed by PA. So we need to move PB towards PA, because to make a node, particular node blue, it should already have been blue. So we should try to make PB go towards PA. We should find the first intersecting point of a blue and red node. So in this particular tree, what I'm gonna do is that I'm gonna move PB in the first operation. In the first operation, first step I'm gonna move PB to this node and PA to this node. And so this is white now, this is red now, and in the next step I'm going to move PB to this node. This node is already already red, so it will become blue, and I'm going to move PA to this node. Okay, So this became blue as we wanted. So what we have to do, the first observation is that we have to uh, bring PB and PA together. We have to bring PB and PA together, and we have to find the minimum distance required to do so. After we bring PB and PA together using the minimum number of operations, we don't need to consider PA at all. We just need to consider PB. That's it. Because like, okay, so now in the condition that in the case that we consider, now PB is over here, right? PB is over here, PA is over here, PA is over here. Now we have to find the minimum number of steps required by PB to visit all the nodes. And why now you will be asking, why don't we need to consider PA now? Why are we not considering PA now? Okay, we are not considering PA because we can make PA move towards the nodes that PB is moving towards. Okay, like we can predict the future for PA, and in the past we can make PA move towards the nodes that PB would be visiting in the future. So suppose like from here we made PA move towards over here, but suppose PB is over here, right? But suppose the optimal move for PB was to go towards here. The optimal move for PB was to go towards here. Instead of making PA go towards here in the previous move, we could have made PA go towards over here, right? So we are predicting the future. So PB would have PB has a better move to go over here. So we are predicting the future for PA that okay, you should go over here as well. So we can predict the future for PA according to the optimal moves for PB in the past itself. So so there is no need to consider PA, since PB is the one that's going to be turning all the nodes blue, and PB is the one that's going to be turning all the nodes blue. We will not consider PA after finding the minimum intersection point between PA and PB. We can predict the future for PA, and we could direct PA to the nodes that PB will be visiting in the future. So we are neglecting PA after finding the intersection point of PA and PB. After finding the intersection point of PA and PB, now what we will do is that now PB has to visit every nodes in the tree. But what suppose okay, now PB has to visit every nodes in the tree. To visit this node, it has to traverse this edge once, right? So it visited this node. Now to visit this node, now PB is currently over here, right? PB has to go back and go over here. So to visit this node, PB went over here, and now to visit this node, PB went back this node again. So it went through this edge twice. So from this observation, we can make that PB has to go through every edge twice to visit other branches. So suppose PB went through this branch, so PB is going through this branch. PB visited this edge, PB then went to this edge, PB then went to this edge, PB then went to this edge. Now to visit this edge, PB has to go back through this edge, then go back through this edge and go to this edge. So these two edges were visited by PB twice. So we can see that it has to visit every edge twice to visit the other branches. Now for it to go here, it has to go back, and it has to visit this node. So it visited every edge twice. But if we think optimally, we have to visit some of the edges twice, but we don't have to visit every edge twice. So okay, I will show you. So suppose like we visited this branch, and we traversed back this branch. So we visited every edge in this branch twice, and then we went to this branch and we traversed back from this branch. So we visited every edge in this branch twice, and then we went to this branch and we traversed back from this branch. So we visited every edge in this branch twice. Then we went to this node, and we went to this node. Since there is no other node to visit, we visited this branch, this branch, we visited this branch, this branch, this branch, and we went towards over here, and there is no branch to there is no more branch to visit. We don't need to traverse back from this node. We can stop here. We don't need to traverse back. So we are visiting this edge only once now. Earlier when we started from this branch, we traversed this branch twice, but now since we are ending at this branch, we only need to traverse this branch once. We don't need to, there is no need to come back, because we have visited all the other nodes. So that is one observation that we have to make. The last sequence of edges that we visit would only have to be visited once. So we need to find the longest edge from the point of intersection, longest length of edge from the this point of intersection. The longest length of edge, as we can see here, 1, 2, 3, 4. So there is a 4 length edge over here. So if we 4 length edge over here, so if we give priority for this branch at the end, if we say that I will only visit this branch at the end, so what will happen? I will visit this branch first, and I will visit every edge in this branch twice. Then I will go towards this branch. I will visit every edge in this branch twice. Then I will go towards this branch. I will go here. Then I will come back. So I will visit that edge twice. Then I will visit this branch. When I visit this branch, I will go here. I will go here. I will go here, and then I will visit this edge, and then I will come back. Then I will visit this node. Then I will visit this node. But there is no need for me to come back, since we have visited every other node. So hence we can minimize the number of steps that we need. So our earlier assumption was that we have to visit every edges twice. n-1 is the number of edges we are visiting it twice. But the edges that we visit at the end, we don't have to visit it twice. We only have to visit it once. So we will subtract the edges that we visit at the end, and we will try to maximize this. To maximize this d, if we maximize this d, this number of operations will reduce, right? So we will try to maximize this d. So to maximize this d, is very easy. So from the point of intersection, we will find the length of every branch from that node, and we will take the longest length branch and we will subtract it. That's it. That's for the operation after finding the point of intersection. So first, what did we do in the first operation? In the first operation, PA was over here and PB was over here. Since PB is the one who has to make the nodes blue, we will try to initiate that process. But to initiate that process, there should be a node that is red, right? Since it can only turn the nodes which are red to blue, we have to find a node which is red. So we are moving both PA and PB towards each other. So we are moving both PA and PB towards each other, and they meet at this point. and now PB is located at this point. Now when PB is located at this point, now what we will do is that now we will find the longest branch from this point, and we will subtract that from the total 2 into the total number of edges. So 2 into total number of edges minus the longest branch will be the number of operations that we need to perform to visit every node from this particular intersection point, so and we are also using some number of operations to reach this particular intersection point. We have to calculate that as well. So and we have to add that number of operations to reach the intersection point. We have intersection point. Now we have to add it to the number of to the number of edges that we visit as well. So this will be the total number of steps that we perform. Total number of steps that we perform. I will show you the code for this. The code is actually very easy. I have only performed DFS, not much hard data structure or not much hard algorithms. I will show you the code now. Okay guys, now I'll show you the code for the solution that we discussed just now. It's easy only. The code is easy. So first we are inputting the position A and B, where A is the position where PA is located and B is the position where PB is located. And now we are inputting the tree using an adjacency list. Then okay, we are creating 4 distance vectors. I don't know whether we need this much distance vectors, but I created this much distance vectors for my convenience. So this distance vector is the distance of every point from A, and this distance vector is the distance of every point, every node from B. So this distance vector is the distance of every point from every node from A, and this distance vector is the distance of every node from B. And this distance vector is actually the the summation of both the values of both the distance vectors. And this distance vector 3 is used to compute the where we said that we have to find the longest branch from the intersection point, right? So this distance vector is used to compute that. We are using these two distance vectors to compute the distance intersection point. So we will use these two distance vectors to find the point where it will intersect. Okay, so to populate the distance from B, we are using this DFS code. This is the DFS code. So it's actually a pretty standard DFS code. I am using this to compute the distance of every node from B. You can go through it, and in this DFS code, I am using it to populate the distance of every node from A, the distance of every node from A, and I'm using the same DFS code. And in this for loop, I am using to find the summation of the distances between the distance of a node from A as well plus the distance of the node from B. Why am I doing this? I am doing this to compute the node which is at a minimum distance from both A and B. So this will help us find the intersection point. So the intersection point is a node which is at a distance which is uh, minimum from both A and B. And we will store that store that particular node in the smallest value node variable, and to find the smallest value node we are using another DFS code. I will explain this particular DFS code to compute the intersection point. Intersection point is the smallest value node, and we have to find the intersection. I am computing the intersection point using this particular DFS code. I will show you a test case so you can understand how that works. Mm, I had a test case here. Let's put test case. Okay, this is a good test case, I guess. Wait. No, this is not the test case. Okay, I think this test case is good enough. I was checking whether my solutions were appearing in YouTube. So what this DFS call will do is that, so it will initially this first if statement is, if the the node is initially -1, we have to populate it with the current node, but we will populate it with the current intersection point as the current node only if the distance from A to that particular node is lesser than the distance from B to that particular node. Why is this important? So uh, suppose 4 and 8 are A and B. 4 and 8 are the A and B. So for a particular node to become blue, first it has to be reached by uh, reached by PA, right? Only after reaching only after a PA reaches a particular node, it will turn red. Only after that, if a PB piece reaches that node, it will turn blue, right? Only after piece reaches that node, it will become red. And only after that, if the PB piece reaches that particular node, it will become blue. So if PB piece reaches a particular node before PA, there is no effect on it. So suppose, like, if this is PB reaches this particular node uh, before PA, so it's still white, so there will be no effect on it, so there is no use considering that particular node. Only if PA has reached that particular node before or at the same moment as PB, that node will change its color to blue, and we can then consider that node as an intersection point. That's why we are checking here. So we are checking whether the distance to that particular node is less, distance of that particular node from A is lesser than the distance of the particular node from B. So whether A can reach a particular node faster or at the same time as B. If it reaches at a later time than B, there is no use reaching that particular node, right? So say the color of the node will not change. And if the else if the value of the smallest val node is not is some value greater than -1, we will check whether the distance to the particular node that we are considering is lesser than the already selected uh, the distance to the already selected smallest value node. So suppose we chose this node as the already existing smallest value node. What is the distance to this? Distance to this from both, the combined distance to this from A and B is 1 2. That's the distance from A. 1 2 3 4. So 2 plus 4, it's 6. So the combined distance from A and B to this particular node is 6. But if we consider this particular node is 1 2, and from B the distance is 1 2. So total distance is 4. 4 is much lower than the distance to 6, right? The distance to the node number 2 is much lesser than the distance to node number 6. So we will update the new smallest value node as 2. And also we have to check whether the distance to 2 from A is lesser than or equal to the distance of 2 from B. What's the distance to node 2 from A? It is 1 2. And what is the distance to node 2 from B? It's 1 2. So it's both distances are equal, so the both A and PA and PB will reach this particular node at the same time, so it will turn blue. So there is no problem considering this particular node. I will show you a counter. I will show a counter node to this particular, particular condition. So if we consider 3, what is the distance to the node number node 3? What is the distance from A to the node 3? It is 1 2 3. And what's the distance to node 3 from B? It is 1. So PB will reach this particular node much earlier than PA will reach this particular node. So there is no use of considering that, because it will still turn us white. But then you will say that, okay, suppose okay, you are correct, PB will reach this particular node before PA. But PB can do this, right? PB can go to this particular node, then it can go to this particular node, then it can come back to this particular node. Then the number of operations will be 1 2 3. uh, at that time PA will reach a particular node, right? 1 2 3. So PA will reach a particular node if we, you know if we make PB go one node extra and make it come back. Yes, you are correct, but we are adding unnecessary moves to this particular node. When we are adding unnecessary moves, the number of steps is increasing. There is already a node which is at a much in a smaller distance, uh, without adding unnecessary moves. There will always be a node at the intersection between A and B. So there is no use of adding unnecessary moves to this particular, to reach this particular tree, to make it blue. So that's why we are considering it, considering this condition. Then we iterate through, you know iterate through uh, the children, and we call the DFS calls again and again. And and we use this function. So the smallest value node is the node at the intersection point. Now we will find the distance to every node from the smallest value node, and we will store the distance in the vector, in the array distance 3. And we will take the, the maximum, the branch which has the maximum distance from the smallest value node. We will store that in max, and we will subtract the number of edges, 2 into the number of edges minus max. And what is this? This is the number of moves required to reach that intersection point from B. So since B is the since PB is the chess piece that we are considering, so and PB has to reach the particular node, the intersection node, for it to make blue. We are considering the number of moves required by PB to reach the particular intersection node. Here, suppose the intersection node is 2, so we have to, add the number of moves required for PB to reach the intersection point. So we are considering that. So we are adding that to the total number of steps that is required. So this is the number of total number of edges into 2 minus the longest branch, uh, and this is the number of moves required in reaching the intersection point from B. So this is a solution for paint the tree problem. So can you comment down below whether you have understood this problem or not, whether you have understood my explanation or not, and how can I improve my explanation in the future? It would be very helpful for me. Thank you.